Suppose we want to find the derivative of z with respect to t if we have z defined as the arctangent of y over x, where x is e to the t and y is 1 minus e to the negative t. Now, of course, these are relatively simple functions, so if you really wanted to, you could substitute in our expressions for x and y to get z as an expression entirely in terms of t, and then apply Calc 1 techniques to find this derivative. But we want to try out our multivariate chain rule here because, sometimes problems are much more complicated, and we would rather not substitute in those values for variables because that could just give us a hideous mess to have to deal with. It's often nice to be able to deal with things in smaller, kind of bite-sized chunks. And also in practice, sometimes we don't have complete information about all of these functions that allow us to do those substitutions. We might have information that comes from observed data, for instance, and just have to work with that. So we'll use this as a relatively simple example to get our feet wet. Before I dive into the chain rule for multivariate functions, let me first discuss a few things about the chain rule for single variable functions. Back in Calc 1, when you first learned about the chain rule, you probably talked about situations where, for example, y is a function of some intermediate variable u, and u is itself a function of the independent variable x, right? And if we wanted, we could draw a sort of dependency diagram showing that y at the top here depends upon the variable u, and u depends upon the variable x. Okay? And at each stage, we have this sort of relationship here. Now, if we change x a little bit, then that's going to cause a small change in u, and that in turn is going to cause a change in y, and the amount of change will depend on the derivatives. So as a simple example, suppose u happens to either be a linear function or maybe just at this particular location that we're concerned with. Maybe any change in x has twice that change in u, and maybe any change in u has 3 times that change in y. Well, now if we change x a little bit, that change is going to get doubled, and that change is going to get tripled. So in the end, we will have 2 times 3 or 6 times that change in y, right? Then this is basically an expression of the Calc 1 style chain rule that says that dy by dx is equal to dy by du times du by dx. Now, thinking of these as differentials, we can see that the du's would cancel and simplify down to dy by dx. And also, looking at this diagram, we can now see why it is that we would want to multiply these two derivatives here, right? Dy by du would be a measure of how much does y change as a function of a small change in u, and du by dx is a measure of how much u changes when x changes a tiny bit. So if we change x and want to know how much y is going to change, that's why we would then multiply both of these together. We have these two derivatives in a chain. There's a chain or sequence of dependency here, and those get multiplied. If we had a longer chain with more levels, more of these nested composite functions, we would just need to multiply together the derivatives at each stage, each step or link along that chain. That's what we're talking about here. So if we come back to this multivariate setting, now our variable z depends on two different variables, x and y. But x only depends on the single variable t, and y only depends on the single variable t. So if we draw a dependency diagram, we can see something like this. Now, some people like to not repeat variables, so if you want to, you could draw this more like this, where you have x and y both coming back together to make t. That's fine. Some of the more complicated examples might get a little bit tougher to follow if you do that, but you can certainly do that if you prefer. I'll leave that to the side, though. I find it's usually easier to keep track of what's going if we have completely separate paths forming an actual tree in the graph theory sense. But this diagram shows us all of our dependencies here. So what this tells us is that if we want to find dz by dt, we can take a look at this diagram to see, well, if we change t a little bit, what's going to happen? Well, one thing that's going to happen is that change in t is going to cause a change in x, and that change in x is going to cause a change in z. So there's this particular path right through here, where if we have this, this first link here, z depends on x, but only in part. Z depends both on x and in y. So this amount of change is going to be a partial derivative of z with respect to x, and that is going to be multiplied by the derivative of x with respect to t. Now x only depends on t, so that's an ordinary derivative, dx by dt. Okay. But this is not the only way that t influences z. We see that there's this other path over on the right here. It also passes through y. And if we look at that, we have the partial derivative of z with respect to y multiplied by the derivative of y with respect to t. Again, this is an ordinary derivative because y is just a single variable function. Y only depends on t. So we have this path from z down to t, partial of z by x times partial of x by t. Sorry, ordinary derivative of x by t. I misspoke. Down this other path, we have partial of z by y times dy by dt. Each of these is going to affect a change in z, so the total change in z will be the sum of those. Each path contributes some amount of change, and those will combine together appropriately in the end. So this little diagram tells us how to construct our chain rule here. Now, it is possible some students prefer to write simpler notations for these. So if you want to write this instead as something like z sub x times x prime plus z sub y times y prime, that is technically acceptable and it's much more compact. However, I feel like it loses some of the checks and structural arrangements that we get with the Leibniz notation. Again, going back to the single variable version from Calc 1, like I mentioned, when we have actual differentials, we can imagine canceling those differentials. We see there's this du that matches here, and we would be left with the dy by dx. Now, when we have partial derivatives, we can't cancel differentials. These partials are not differentials, so they don't cancel. But you can see that we still have this structure where we have these dx's matching and these dy's matching. They aren't both actual ordinary d's, but we have these x's and y's, and you have this idea of z and t being associated. So we have z going through x to t, and z going through y to t. Right? So you might find this full arrangement like this easier to construct and read and make sure that everything is arranged adequately. But anyhow, whichever way you write this, we now that we know which partials we need and how to stick them together, we can evaluate the derivative that we're looking for. The derivative of z with respect to t will be the partial of z with respect to x. So we look at our definition of z right here and think about holding y constant and x as variable. This is a derivative of an arctangent, so it is 1 over 1 plus the argument squared. And that will be multiplied by the derivative of y over x. Let's see, that's an x to the negative first there, so that looks like negative y times x to the negative second for that derivative there. You'll note that I had to use the ordinary chain rule from Calc 1 to complete this evaluation. But we're thinking of z as just being a function of x temporarily for the purposes of this partial derivative, so we apply that ordinary chain rule there. Now our chain rule tells us that we need to multiply this by the derivative of x with respect to t. Well, x is a fairly simple function. The derivative of e to the t is e to the t. So that works just like that. Now we need to add, looks like I'm going to run out of space, so let's do this down below. I need to add the partial of z by y. So we again look at our definition of z. Once more, that is an arctangent on the outermost function, so that is 1 plus y over x quantity squared. But then the ordinary Calc 1 style chain rule tells us we need to multiply by the derivative of what's inside. Now x is constant, so we just have y divided by a constant. The derivative of that with respect to y is just 1 over x, or I'll write that as an x to the negative first here. That is partial of z by y. And now we're multiplying by dy by dt. Derivative of y with respect to t, we would have negative e to the negative t times negative 1, so that looks like e to the negative t, if I have think about all of that correctly. So now we have this expression here. We have our partial of z by x times dx by dt plus the partial of z by y times dy by dt. All that's left now is to clean this up, do some simplifications. We see this same denominator in both of these, so let's go ahead and add these together. It looks like we have negative y x to the negative second e to the t plus x to the negative first e to the negative t divided by 1 plus, and that is basically a y squared over x squared. We see we have a lot of negative exponents, and in particular reciprocals of x. So let's get rid of some of these compound fractions. We have x squared in the denominator, we have an x to the negative second. So let's multiply by x squared over x squared and see what that does for us. Let's see, that's negative. Let's bring this term here forward. X squared times x to the first is x. So we have x e to the negative t minus y, the x squared times x to the negative second is 1. We have an e to the t. And this is divided by x squared plus y squared, it seems to be. Right? So clean that up a bit. We do still have this e to the negative t in here, so technically this is still a compound fraction. We might consider multiplying numerator and denominator by an e to the t to get rid of that. But in this case, we see that that is actually going to not help a whole lot, right? We'll get an e to the 2t there, then we'll have this extra factor of e to the t down here. That doesn't actually clean things up. So let's not do that, and we can just leave this in this form here. This seems like a reasonable way, probably, you know, kind of a 6 of one, half dozen of the other kind of situation, or a pick your poison, whatever idiom seems appropriate there. But this seems to be, on balance, the simplest and most symmetric way to write this derivative that we found. Okay, so hopefully you can kind of see what we're doing here and how we can construct a little diagram of dependencies, and that diagram can help us track through which things we're looking for. You know, so keep that in mind as you go through the examples in this section. Build those little diagrams, keep track of what things depend on what, and how we can use that to write the appropriate chain rule. I suppose with sufficient practice, you might need only one of these or the other, right? You might find that you don't need the diagrams eventually, and you can just write the chain rule because you see how to track through the dependencies mentally. Or alternatively, you might prefer to write the diagrams and find that once you've written the diagram that you don't need to actually write out the chain rule for your applications. For the purposes of this class, you should always write out the chain rule at least to make it clear what you're doing, so that it's easy for anybody grading your work to tell what you're actually evaluating and make sure you're doing each of those derivatives correctly. But when it comes to just doing your own work later on, you'll probably find that one or the other of these will be sufficient. But at the beginning, I recommend doing both. Practice drawing the diagrams, use that to construct a written form of the chain rule, however you want to write it, and then use that to guide your evaluations of derivatives along the way. Substitute, simplify, and there you go.